Hi, my name is Liudmila, and in this presentation, I'll tell you how to estimate predictive uncertainty in gradient boosting models. This talk is based on a joint work with Andrei Malinin and Alexey Ustimenko from Yandex Research. In certain high-risk applications, such as autonomous driving, medical diagnostics, and financial forecasting, the cost of a mistake can be huge. In these applications, it is important to detect when the system makes a mistake and act accordingly. Take safer actions, ask for human intervention, or teach the system to make correct predictions through active learning. The choice of action can depend on why the model is uncertain. There are two main sources of uncertainty: data and knowledge. Data uncertainty reflects the noise of the target label for given features. This uncertainty cannot be reduced. Knowledge uncertainty comes from the lack of training data in a particular region. This uncertainty can be used for active learning and can be reduced by collecting more training data. Here you can see an example of data uncertainty. The task is to classify images into cats and dogs, and a cat-dog is given as an input. This presentation is about uncertainty estimates in gradient boosting. So, let me briefly describe the algorithm. Gradient boosting is a method of building a strong model from weaker ones. Namely, assume that we are given a set of weak learners H. Usually, this set is formed by shallow decision trees. At each step of the algorithm, we compute the gradient of the loss function with respect to the current predictions. Then, we approximate the minus gradient by a weak learner from the family H. Finally, we multiply this weak learner by the learning rate and add it to the current model. After t steps, we obtain a strong model Ft. Informally, this procedure can be thought of as gradient descent in a functional space. As I mentioned, the set of weak learners is usually formed by shallow decision trees. At this slide, you can see an example of such tree. To make a prediction, we go from top to bottom and check the conditions in the corresponding nodes. The leaves contain the model's predictions. So, we want to estimate predictive uncertainty in gradient boosting models. Let us start with data uncertainty. For classification, models are usually trained with the negative log likelihood or cross-entropy loss. As a result, each prediction is a distribution over the class labels. Using this distribution, we can estimate data uncertainty as the entropy of the distribution. In contrast, regression models usually yield only point predictions. This problem was recently addressed in the NGBoost algorithm. To estimate data uncertainty, we can assume the normal distribution of target conditioned on features and optimize the negative log likelihood. This will give us estimates of mean and variance. The variance of this distribution is data uncertainty. Now we know how to estimate data uncertainty. But how to measure knowledge uncertainty coming from the lack of training data in a particular region? Estimating knowledge uncertainty requires an ensemble of models. This technique is successfully used for neural networks. Assume that we can sample several models from the posterior distribution. If all the models understand an input, they will give similar predictions, which corresponds to low knowledge uncertainty. However, if the models do not understand the input, then they are likely to provide diverse predictions and strongly disagree with each other, which indicates high knowledge uncertainty. This slide formally defines knowledge, data, and total uncertainty for classification and regression. For classification, data uncertainty can be quantified as the average entropy of individual models. Knowledge uncertainty is the mutual information between the model's parameters and the prediction. And total uncertainty is the entropy of the average prediction. For regression, data uncertainty is the average predicted variance, while knowledge uncertainty is the variance of predicted mean values. Okay. To quantify knowledge uncertainty, we need ensembles. How can we generate ensembles of gradient boosting models? The simplest way is to consider an ensemble of stochastic gradient boosting models. At each iteration of SGB, we select a subset of training examples to fit the next tree. This implicitly injects noise into the learning process, so we can get an ensemble of random models. Let us note that each SGB model is an ensemble of decision trees, and we further generate an ensemble of such ensemble models. Let us note that there are no guarantees on how well the distribution of these models estimates the true posterior. Notably, there is a way to sample gradient boosting models from the true posterior via a recently proposed stochastic gradient Langevin boosting. This algorithm is an easy-to-implement modification of SGB. The model's parameters are known to converge to the invariant measure P star. Initially, this fact was used to prove the global convergence of SGLB even for non-convex functions. However, we use it for a different purpose. If we properly set the parameters of the algorithm, we can note that P star becomes asymptotically proportional to the true posterior. So we can generate an ensemble of several independent SGLB models and guarantee that they are asymptotically sampled from the true posterior. In practice, training an ensemble of several models can be too expensive. Ideally, we would like to train a single model but still be able to detect outliers. There is a solution for that, and we call it a virtual ensemble. Such an ensemble can be obtained from any trained model. The main idea is shown in this figure. We exploit the fact that a single SGB or SGLB model is an ensemble of trees, so we can use truncated models as ensemble elements. In this case, we get an ensemble of models without any overhead in memory and time, both for training and inference. However, ensemble elements are correlated, which may lead to underestimated knowledge uncertainty. To illustrate the discussed concepts, let me show two simple synthetic examples. In the first one, we generated a discrete regression dataset where each example is described by two categorical features. Each feature has 9 values. For each training example, we sampled the target from a normal distribution with parameters defined by features values. The mean value is randomly generated, and the variance is shown in this figure. In the white region, inside the heart, we have no training examples. We train an ensemble of SGLB models on this dataset. On figure B, we show the estimated data uncertainty. We can see that data uncertainty captures the variance everywhere except for the empty region. We have no training data to restrict predictions inside the heart, so anything can be obtained there. Then we plot the estimated knowledge uncertainty that perfectly captures the out-of-domain region inside the heart. In the second example, we generated a continuous classification dataset shown on the slide. This setting is much harder for gradient-boosted trees. To partially mitigate the difficulties, we use coordinate in rotated axis and radius as additional features. Again, we apply an ensemble of SGLB models to this data. Figure B shows the estimated total uncertainty that correctly detects class boundaries and sectors of input space outside the training dataset. Looking at these sectors of high uncertainty, we can better understand how GBDT ensembles work. If features have values outside the training domain, then the prediction is the same as for the closest elements in the dataset. In other words, the model's behavior on the boundary of the dataset is further extended to the outer regions. Then we plotted the knowledge uncertainty. We can see that it allows us to discriminate between out-of-domain regions and class boundaries. However, we can still see the traces of the class boundaries in figure C. A possible reason is that for real-valued features, the splitting values may vary near the class borders, resulting in non-zero estimates of knowledge uncertainty due to decision boundary jitter. Then we compare true ensembles on the left with virtual ones on the right. For the discrete hard dataset, both of them detect the region of high knowledge uncertainty equally well. In contrast, for the continuous spiral dataset, the virtual ensemble struggles to separate the outer region from the class boundaries. Finally, let me show how knowledge uncertainty helps in detecting anomaly examples. For this purpose, we took several classification datasets and added out-of-domain inputs to their test sets. For each measure of uncertainty, we used the area under the ROC curve to see how well it captures such anomaly inputs. We can see that the ensemble methods outperform single models. Also, as expected, out-of-domain inputs are better detected with knowledge uncertainty. Finally, virtual ensembles usually perform worse compared to ensembles of independent models. However, virtual ensembles are still much better than single models while having the same time and memory complexity. Let me conclude with what we've learned. To estimate predictive uncertainty, one can use ensembles of GBDT models. For regression tasks, data uncertainty is the average predicted variance, and knowledge uncertainty is the variance of models' mean values. For classification tasks, data uncertainty is the average entropy, and total uncertainty is the entropy of the average prediction. If you are looking for the easiest way to estimate uncertainty with your gradient boosting model, you can try CatBoost, an open-source GBDT library. CatBoost has several tools for quantifying predictive uncertainty. First, the loss function RMSE with uncertainty predicts the target's mean and variance for regression tasks. Second, there is an option posterior sampling that turns on SGLB mode and sets learning parameters to guarantee the posterior sampling. Finally, there is a prediction type word ensembles that allows getting the predictions of the virtual ensemble given only one trained model. Here you can see some references used throughout the presentation. That's all. Thank you for your attention.